Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series where we are discussing all the chapters. We have started with second PU chapters. We have already completed I guess 8 chapters. This is the 9th chapter, wave optics. So let's start with the chapter wave optics. Here we are going to discuss the entire chapter. Wave optics used to be a big chapter, but now a lot of part is deleted, so we are going to discuss only the part that is there in the current syllabus. We will not be discussing anything which is out of syllabus. Maybe that is there in JEE exam, maybe that part is there in NEET exam, but since we are dedicatedly focused only on KCET, we are not going to discuss anything which is out of syllabus. Also, every Sunday we are conducting a test. We are calling it KPL, KCET Premier League, and that is going to happen this Sunday. If you have missed previous sessions, don't worry. Only thing that you have to do, you have to join our WhatsApp channel. In our WhatsApp channel, every Sunday in the morning, you will receive the question paper. You have to download the question paper, solve the question paper, and at the night, I'll be back with the solution of entire question paper. So that will be a good practice for you. And if you are not participating in KPL, which is absolutely free, you are losing on a chance that to prepare for KCET 2025. I know many of you are wondering if I should prepare for JEE or I should prepare for KCET. Remember that KCET focused on Karnataka students, and you have a better chance, much better chance than JEE. So if you are thinking for JEE or NEET, better you have to first prepare for KCET, then you can think about JEE and NEET. Okay. Now let's start with the list of contents. What all we are going to discuss. We are going to start with Huygens principle. Then we will discuss coherent and incoherent light. Then we will discuss Young's double slit experiment. Now in this part many concepts are now deleted, but we will be covering what all are there in the syllabus. Also I will mention what all deleted now. Then we will discuss diffraction. Here also a lot of concepts are deleted. And then polarization. Okay, every year 3 to 4 questions comes from this chapter, so don't ignore this chapter. You have to study the chapter in detail. Even though the parts are deleted, there are still a lot of possibilities that might come in your KCET exam. We will see some questions from your previous years which are still part of the syllabus, so don't go anywhere. Be seated throughout the lecture. Let's start with Huygens principle. Okay, so before Huygens principle, there is a very important concept, is wave front. Okay, so before I start, I should let you know that so far whatever we have studied light is traveling in a straight line. Okay, also in electromagnetic wave chapter we have learned that light is a wave, right? Now wave and straight line does not go hand in hand, right? So if you know, straight line means this is a straight line. Wave means this, right? So how can this be a straight line? This is obviously not a straight line, but since the wavelength of light is very small for human eye to comprehend, okay, we consider this is the mean path of the ray as straight line. And all the things in geometric optics, whatever you have studied, there we have studied about straight line, right? Rectilinear propagation of light. So the lens, the mirrors, the refraction, the diffraction, everything we have considered using a ray of light, right? So straight line propagation of light. There are few incidences, few things that is not possible to explain using conventional ray optics. So that's why there was a physicist called Huygens. Okay, there are different theories about light. Even Newton had a corpuscular theory which was later rejected. But Huygens principle, Huygens was one of the few who said that light is actually a wave. Okay, that point of time light was not considered as a wave, so he said it is not only a wave. Okay, he gave the definition of wave in terms of wave front. So what is the meaning of wave front? Let us understand that. Suppose you are standing in a pool, okay, or a pond, or a pool, a pond, whatever, a river, okay, a water body or a bucket of water also will do. Now you take a stone, you throw it on the pond. Okay, then what you will see? you will see that there are certain circles forming around the position where you have thrown the stone, right? So it will be like this. There will be a ripple effect. This is called ripple. Okay, so the ripple will transform in all the possible direction, right? Now here amazingly what is happening here is all the waves that is generating from this position, they will all have the top position, that is the crest. We call the crest of the wave. Crests are all forming at a single line. Okay, single line. Here not a line, here it is a circle, but circle is also two-dimensional way. So right, so we can say that they are all, you can connect all the position which are all high or all low at the same time, right? So that thing, that line which connecting all the points in that same phase or same way they are generating, they are called wavefront. Okay, so wavefront is defined as the surface of constant phase. Constant phase means, suppose I am saying that there is a source. Okay, from there light rays is starting or some wave is starting. Okay, so this is the first peak, this is first peak, this is first peak. Now these all points are in same phase. Similarly, this is second peak, this is second peak, this is second peak. They are all at same phase. Phase means they are all having the same time difference or same path difference from the source where they have started. Okay, so suppose you start from your college, all the friends decided, okay, I will be going to home from our college. So each steps you are taking, okay, each of you are at same phase. Okay, so you are going towards left, someone is going towards right, someone is going straight. But if you are moving with the same speed, which is possible because light always travel in the same speed, okay, in a medium. So if you are traveling in the same speed, after 5 minutes each of you will have the same phase. Okay, so even though you are moving in the different directions, there will be, all of them will be in the same phase. I can give you one more example. So you are currently studying in second PU, right? After 1 year you will move to first year. Whatever you study BSc, you study engineering, you study doctor, whatever you do, after 1 year you will be in the first year of that course, right? And your friends, your classmates, all those who qualify along with you, so qualification is the starting point, all those who qualify the second PU exam, they will also be first year of something, right? So they are all in the same phase. So you are of the same batch 2024-2025, right? That thing never ever leave you. You will be always the batch of 2024-2025. So for example, those who have passed during 2020 and 2021, they are called COVID children, COVID batch, right? So COVID batch means they all started during COVID. So similarly, light rays are also having similar phase relationship. So this is called phase. Phase means they are started from a position and they moved some distance after a fixed amount of time. Then they are all having the same strategy. They are all the same position, right? If everything is peak, they are all at peak. Everything is crest, everything is at crest, right? So that is the basic meaning of phase. Very important concept. You have to understand. If you still don't understand, you can mention that in the comment below. I will try to explain it using once more. But now, so it is also sometimes called locus of the all points at same phase. Locus is a mathematical term. If you are familiar with locus, okay, straight line, hyperbola, parabola, there we define them as a locus of some point, right? So here locus of all the points having same phase, that is a mathematical definition of wavefront. Now the speed with which the wavefront moves outward from the source is called the speed of the wave, right? So speed at which the wave moves from the source is called speed of the wave. So every wave has a fixed speed in a same medium, right? So all the waves are traveling at the same speed. Let me erase this outer one. Now let's look into the Huygens principle now. According to Huygens principle, each point of the wavefront is a source of secondary disturbance, and the wavelets, wavelet means children waves, children wavefront, okay, each wavelets emanating from this point, emanating means emitting, okay, emanating from these points spread out in all direction with the speed of the wave. Now I will give you basic idea about Huygens principle. So let's see. So suppose there is a source, okay, we have a source here and light ray is traveling, say, in this direction. After some time t, they all reach along this direction. This is the pool that I said. So when you drop the stone on the water, they all form circular pattern. So this is the circular pattern, right? So they are all at same phase. So you can consider this as a wavefront. This is a wavefront. This is a wavefront. Right? Now Huygens principle says that each point on this wavefront, each and every point on this wavefront are actually source of secondary wavelets. So they are all source of secondary wavelets. What is the meaning of that? So secondary wavelets means you can consider each of these points as secondary sources of light, right? So light starts from here. This is the source, this is the torch. Suppose you are lighting a torch towards someone, or there is a tube light which is giving you light, or a bulb, or anything, a CFL or a mobile torch, whatever it is, this is the source of light. Now when you switch it on, all the lights coming from this, they are moving in some direction and they are forming a wavefront. It is an invisible thing, it's a hypothetical thing, it does not exist in you cannot see that in reality because light itself is invisible. We know that, okay, light when falls on something, it makes that thing visible, okay. So that's why we cannot see the wavefront actually, but we can see wavefront when we drop a stone on the water. The circular patterns that you see, that is nothing but a wavefront, okay. Now Huygens says that each of the point on that wavefront are sources of secondary wavelets, okay. What is the meaning of that? Each point on this line, they also emanate light in all possible directions. So this is a secondary source. This is also sometimes called secondary source and we denote it by S dash, okay. They also throw light in all possible direction, okay. So basically this is the meaning of Huygens principle, that whenever we consider a secondary wavelet or secondary source, from there light also emit as if it is moving in all possible direction. Now there is a drawback of this law. Obviously if this is to be 100% true, then we can see the source even we are facing opposite direction of the source. So for example, there is a light behind me, okay, I can see the light only when I am facing it, or maybe at some angle, up to certain angle I can see the light. But if I face it completely opposite direction, will I be able to see that light? Obviously not, right? So but according to Huygens principle, so light is coming here, okay, and here suppose there is a wavefront. From this wavefront, light is propagating in all possible direction. That means I should be able to see that light because some light from this light which is behind is coming towards me. But if that is happening, then I would be able to see that tube light even if I am facing the opposite direction, right? But that is not happening. So there is a catch. So there was another physicist, he corrected this equation and later on it was called Huygens-Fresnel principle. So we are not going into that detail, okay. He added a term, so that is the correction, Fresnel's correction, but that is a little bit higher level for you, okay. But you should remember that this law is almost 95% correct. You can assume that this is almost 95% correct. So 95% correct. So we can assume, okay, we have in some cases we have even considered less corrected the things as okay. So we are okay with this formula for now, okay. So this light spreads out in all directions with the speed of the wave. So if this is a light, then, and if you are considering vacuum, then speed of light here is c. So all these lights are also emitting with speed c, okay. They are also emitting with the speed c, okay. So there is a question, I will see that in a while. Now these wavelets emanating from the wavefront are usually referred to as secondary wavelets. Okay, and if we draw a common tangent to all of these spheres, we obtain the new position of the wavefront. So what is this? So this was the secondary wavelet. Light is traveling in all possible direction. Now if we draw the tangent on that, that is basically another circle, then when all of these secondary wavelets they meet and you draw a tangent to that, you get the position of the new position of the wavefront. So if you consider this time difference is delta t, then after delta t, what will be the shape of the wavefront? The shape of the wavefront will be another circle, right? Now it depends on the type of the source, the shape of the wavefront we will discuss in a while. But first let us look into a question. When light propagates through a given homogeneous medium, okay, the velocities of primary wavefronts are lesser than those of the secondary wavelets. Primary wavefronts are greater than or equal to those of the secondary wavelets. Primary wavefront and wavelets are equal. Primary wavefront and larger than those of the wavefronts. Okay, so we know that they are always equal. The speed of the velocities or speed of the primary and secondary wavelets are always equal. They all travel with the same speed, that is speed of light. Now if there is a point source, if the source is point, then light will be propagating in all possible direction. So all possible direction means right, left, up, down, forward, backward, and the shape of the wavefront will be a sphere. Okay, it will be a spherical wavefront. So sometimes you may have heard it, it is called spherical wavefront. Sometimes this related question also comes. And if the source is like a tube light, okay, that is a extended line source, then the shape of the wavefront is basically cylindrical. Okay, the shape of the wavefront is cylindrical. Concentric cylinders will be the wavefronts. In this case, concentric spheres will be wavefront. Okay, so for line source, the shape of the wavefront is cylindrical, and for point source, the shape of the wavefront is spherical. You should remember these two as well, along with whatever we have learned. Now, for light diverging from a finite point source, the wavefront is parabolic, as I said. Now, this is also from your previous year question. The wavefront is cylindrical. The intensity of the wavefront does not depend on the distance. The intensity decreases in proportion to the distance squared. Now, even though these wavefront related options are incorrect, there are certain option that is correct. So when you are moving, suppose this is your source, point source, finite point source. Okay, so finite point source means the light will be obviously spherical in nature. Okay, a finite point source, the source will be obviously spherical in nature. So these two options are obviously incorrect. Okay, now what about intensity? As you are moving from the source, okay, and you are trying to find the intensity at a point. Okay, intensity means how bright the light is at that point. Intensity basically refers to how bright the light is. For example, if you see a light from a very distance, it appears like dim. You can just see it. It is dimming. Just we say, okay, there is a something is there, right? But as you go closer, you see there is a house, there is a light, etc., etc. Right? So similarly, as the distance increases, the brightness of the source decreases. Right? So the brightness is changing with the distance, and the brightness or intensity is basically inversely proportional to the distance, square of the distance. So more far it is, more or less intensities. Okay, so this intensity of light decreases rapidly as you are moving away from it. So very, very important concept. So that is also we have covered. Now let's move into coherent and incoherent sources. Okay, so let us first look into coherent sources. What is the coherent sources? Suppose we have two sources, S1 and S2. Okay, and two brothers. We have two brothers, S1 and S2. Okay, if when S1 is sleeping, S2 is also sleeping. When S1 is awake, S2 is also awake. when S1 is eating, S2 is also eating. So whatever S1 is doing, S2 is doing the same thing at the same time. So when S1 is studying, S2 is also studying, right? If S1 is going to college, S2 is also going to college. So two students, when they are doing everything similarly, they are called coherent students. Similarly, two sources, okay, if they have a particular phase difference, okay, they need not to do everything simultaneously, even if there is a time gap. So for example, if S1 wakes up say at 7 a.m. S2 wakes up at 7:05 a.m. Okay, S1 brushes his teeth at 7:15 a.m. Okay, S2 does that at 7:20 a.m. Okay, S1 goes to study at 7:30 a.m. Okay, S2 goes to study at 7:35 a.m. Okay, S1 then have breakfast at 8:30 a.m. S2 also have breakfast at 8:30 a.m. 8:35 a.m. sorry. Okay, so after some time, okay, S1 goes to bed say at 11 p.m. and S2 goes to bed at 11:05 p.m. So if you see, after every incident that S1 is doing, S2 is doing the exactly same thing 5 minutes after. So the gap between S1 and S2 is constant throughout the day, right? So we can say there is a constant phase relationship between S1 and S2. That phase difference is 5 minutes. Okay, so whenever it is happening here, it is happening after 5 minutes. So this is called constant phase difference. Similarly, light waves are sometimes, suppose this is starting and this wave is starting after say 5 seconds, and this is continuously going on for a long time, then we say these two sources are coherent sources. Very important concept, the phase difference. Phase difference means the time gap between, suppose it is giving a peak, it is giving another peak. Okay, so two sources, when one is giving peak, another one is giving peak after some time, and this thing is continuous, then we say they are coherent. So two sources which are linked with each other through a fixed time gap, then they are called coherent sources. Okay, so if the phase difference between the displacement produced by each of the wave does not change with time, they are called coherent sources. Okay, and incoherent sources, there is no phase relationship. Obviously, easy thing is incoherent sources. So it does not matter what I am saying here, whatever you are doing here. Okay, if you don't study, don't listen to me, then you are incoherent. But whenever, as soon as I am uploading the video, okay, you are coming every day same time, listening to me, okay, listening to my lecture, commenting on my video, then you are a coherent student. But if you are not doing it, you are doing, okay, so I will check for 5 minutes, then I will skip. So that is a incoherent student. So whatever you are doing, whatever I am doing here, I am a coherent. I am coherent. Every day, same time, I am uploading a lecture, right? But if you are watching that or not, that is up to you. So you are an incoherent student. Okay, I don't know, maybe you are a coherent student. Some coherent student is also observing me, I know. But most of you are watching my videos, they are incoherent. Okay, they come at their own time, they leave at their own time. Right? So coherent is easy. Coherent is disciplined. Incoherent means not disciplined. There is a no phase difference, phase relationship. Okay, so that is the basic difference. So two students, one is sleeping, another one is playing to cricket. Another one is studying, the second one is now watching movie. Third one is studying from YouTube, another one is watching video on YouTube. So they are completely doing different things. Then they are called incoherent, right? Now, the light waves coming out from two independent sources of light do not have any phase relationship, and they are called incoherent. So basically, whatever I am saying is that, so to make a coherent source, two sources, basically coherent means more than one, obviously. So suppose I have two sources, S1 and S2. Now if they are separate, they are individual lights. Okay, so two tube lights you fixed and you are thinking, okay, I have a coherent sources, that will not work. Okay, coherent sources cannot be created by using two individual lights. then how can we create coherent sources? There are certain ways, I will tell you in a while. So there is a way of creating coherent sources as well. Now, before going into that, we have to understand the superposition principle. What is the superposition principle? At a particular point in the medium, the resultant displacement produced by number of waves in that is the vector sum of the displacement produced by each of the waves. Suppose I have a light ray coming like this and another light ray is coming like this. Okay. There is and what is the net displacement? So if this is suppose say x, this is say y. Okay, what is the net displacement? Net displacement means what is the resultant wave. So resultant wave, obviously we know that it will be x minus y or y minus x, whoever is larger. So in this case it is appearing y is more, so it will be y minus x. It will be vector sum of all the waves that is falling at that point. So this is happening at some point. Okay, a wave is traveling from all the direction, 5-6 waves, they all travel in some direction and they combine at some point. At that point, if everyone is going up, the total result will go up massively. If everyone is going down, the result will go down massively. But some is going up, some is going down, then you have to add them up. You have to find if it is up, then it will be positive, if it is down, it will be negative, and then you have to calculate the sum. Okay, this is very important concept for two waves. So for example, here we have two waves, y1, another wave y2. Okay, they are represented by a1 sin omega t and a2 sin omega t. So for example, here instead of considering x and y, I say this is a1, this is a2. Okay, they have, this is the phase difference. This is called the phase difference. Phase difference means whatever it can be. For this, for example, here the phase difference is pi by 2. Pi by 2 phase difference means if one is maximum, another one is minimum. Okay, not only that, their amplitudes are also different, right? So now what will happen if these two waves combine at some point? If they combine at some point, then their relative amplitude means if you add them, there will be a wave called y is equal to r sin omega t plus delta. Some value you will get, some value. Okay, so this r value, the resultant amplitude, will be given by a1 square plus a2 square plus 2a1 a2 cos phi. Very important relations. Sometimes numerical, sometimes objective question comes from this question, and this is also very important for JEE as well. Okay, the resultant intensity is proportional to r square. Now intensity of wave is always proportional to the square of the amplitude. You should remember that. So for example, what is the intensity of y1? Intensity I1 is proportional to, there is a proportionality constant a1 square. What is the intensity of I2? I2 is k a2 square. What is the total resultant intensity? Resultant intensity is k r square. Okay, this is a varies with, this symbol is I varies with r square. Okay, there is a linear relationship with r square. In fact, if you replace in this equation, you can write the intensity equation as I equals to, I is square root of r square. So that is, we can write this as a I1 plus I2 plus, there won't be any root, square root, sorry, you have to square r, right? So I1 plus I2 plus 2 square root of I1 square root of I2 cos phi. Okay, sometimes this based formulas, this based problems comes in JEE. Okay, if you are preparing for JEE, you should look for this equation. Okay, this is there. I have not seen any question in KCET based on this formula, but who knows. Okay, now let's look into interference of light. Now interference, so we say no, he is interfering in my life, he is interfering in my study. So what is the meaning of interference? So there is a beautiful meaning of interference in optics, okay, especially wave optics. And interference is one of the phenomena that cannot be explained in ray optics. Okay, using ray optics you cannot explain interference. To explain interference there are three phenomena actually: interference, diffraction and polarization. These three phenomena you cannot explain using ray optics, you can only explain them using wave optics. Okay, now a phenomenon that occurs when two or more light waves interact with each other, causing the combined amplitude of the waves to increase or decrease. So we have seen that when a light ray is traveling like this, another light ray is traveling say like this. When they are falling, they are superposing on each other. When they are superposing on each other, okay, the resultant wave, they have low amplitude somewhere, high amplitude somewhere. Okay, in fact if both of them have same amplitude, amplitudes, then at some point of time you will get a very high value and some point you will get a very low value. Okay, so that is the redistribution of amplitude of the resultant wave is called interference. So interference means you are overlapping two waves, they are not exactly in phase, they have some phase difference, and due to that, okay, what is happening at some point the resultant amplitude is increasing and at some point resultant amplitude is decreasing. So that is called interference. Okay, let us look into this diagram. Okay, here we have two coherent sources, S1 and S2. They are both sending lights towards some point P. We know that according to Huygens principle, also according to the ray optics as well, that light can travel in all possible direction from a source of light. So that's why this is also sending light here, this is also sending light here. Now there is a fixed phase difference between these two lights at this point. So based on the phase difference, we will obtain either very high intensity light or very low intensity light. High intensity light is called maximum, okay, or maxima, okay, for plural. For singular it is called maximum, for plural it is called maxima, and for minimum intensity we call it minima, okay, or minimum. So it is called minima or minimum, right? Now how can we create these two coherent sources? That is what I said I will discuss. So to create a coherent source, what we have to do, we have to take a single source. We have to take a single source. We cannot use two different sources. Now from there we will be having, we suppose we have a plain sheet of paper. Plain sheet of paper, completely dark. I have a source, a light source, okay. Say I have a bulb or halogen lamp, okay, whatever it is, monochromatic, it has to be monochromatic. Now what we have done, we have created two holes on this sheet of paper. Okay, so we have created two holes on the sheet of paper, and this source is exactly at the midpoint of this point, of this line. Okay, then these two sources, these two secondary sources, you can consider them coherent sources. Why? So light from here it will travel here, light from here it will travel in this direction. Now according to Huygens principle, each of these 2 points should behave as secondary sources of light, right? So these are all secondary wavelets, it will emanate secondary wavelengths. So you can consider all the lights coming from this as secondary light. So these secondary sources can be coherent in nature, okay? And there are some experimental procedure, after a long process people have formed coherent laser sources, but that is very expensive, not available. So in our laboratory, when we perform experiment, we create two such small cuts. These small cuts are called slits. These small cuts are called slits. The next experiment, the first person who did that is called Young's. Okay, Young is a name of the scientist, a name of the physicist. Okay, he did the experiment, the same experiment, same diagram that I have shown to you. Okay, this experiment, basically there was a point source somewhere here, and from that point source light ray is going there, and from there it is happening, and this experiment is called Young's double slit experiment. Okay, Young's double slit, because we have two slits, one single slit is 1, 2 means double, so that's why it is called double slit experiment. Now in the double slit experiment we obtain maximum and minimum, okay, based on certain condition. So as I said, suppose this is my source S1, this is my source S2, and I am observing somewhere here, okay, this is the central line, this is the central line, this is called origin, okay, and at the center, both the rays coming from here, they are traveling the same distance, so they are interfering at this point at same phase. Okay, at the center of this line, both sources are sending light at the same time, so they are coming with the maximum intensity. For in Young's double slit experiment, here we always obtain a maximum, and it is called central maximum. Okay, central maximum stands for the maximum that is occurring at the center of the fringe, center of the screen. Okay, and these all, once they are placed on a screen, you will obtain alternative dark and white bands. Band means friendship band, you have seen. Similarly here also you will obtain one dark band, then one bright band. Okay, so I am representing bright band with the cross and a dark band like this. So suppose this is my central maxima. So on both sides of the central maximum you will obtain one dark band, one white band. Okay. So as I said, when they are giving you the maximum intensity, I told you they are called maximum, and when they are giving minimum intensity, they are called minimum, right? And there is one more. When you are getting the bright band, they are also called constructive interference. Okay, this is also an alternative term. This is called constructive interference, and where you are getting dark bands or lowest intensity, that is called destructive interference. Okay, you should remember this. Now, what is the condition for maximum? What is the condition for minimum? So this is called, the central fringe is generally denoted by n equals to 0. So if you have the central fringe, it is called n equals to 0. Now you have a screen which is located at a distance capital D, and the distance between the sources is small d. So the distance between the sources is small d. The distance between the screen and the plane of the source is called capital D. Suppose you are measuring what will be the whether it will be a maximum or minimum at some distance x from this point O, then, and the wavelength of the light used, say lambda, then if it will be a constructive interference or a maxima if they satisfy this relation. Okay, xd by d equals to n lambda. So you have to multiply x small d, okay, divided it by capital D, then you will, if you get any integral multiple of lambda, okay, integral multiple means if it is 1 lambda, 2 lambda, 5 lambda, then we can consider it as a constructive interference. But if it is 1.5 lambda or anything in between lambda, okay, say 1.7 lambda, 1.9 lambda, then it will not be a constructive interference. Okay, but for most of the parts the values will be given. What you have to do, you have to calculate the n value. Okay, we'll see one numerical. Okay, this is called the condition for constructive interference. There is also condition for destructive interference. For destructive interference, that is the dark bands. So this is the condition for constructive, this is the condition for destructive. Okay, for destructive interference, xd by d equals to n plus half lambda. Okay, very interesting question, very interesting concept. Okay, so we will see one problem. So how can we apply that? So in Young's double slit experiment, two wavelengths, lambda 1 equals to 780 nanometers and lambda 2 520 nanometers are used, okay, to obtain interference fringes. If nth bright fringe bright band due to lambda 1 coincides with n plus 1th bright band. Now the bright band or dark band is also sometimes called fringes, okay, so be careful. Bright band due to lambda 2, then the value of n is. So what they have said? They have said that we know that what is the formula? xd by d equals to n lambda, right? Now they have said everything is same. Everything is same except that for one wavelength we are getting nth bright fringe, nth means fifth, suppose fifth bright fringe, and for the second wavelength we are getting n plus 1th bright fringe, that is 6th bright fringe, okay. So everything on our left hand side is constant, but on our right hand side, for first case if we get n lambda 1, then for the second case we are getting n plus 1 lambda 2, right, n plus 1 lambda 2. So now we have to put the values of lambda and solve it. Lambda 1 is 780, n plus 1, lambda 2 is 520. Okay, now both are nanometers, so we do not need to convert the units. 780 n equals to 520, or let me reduce these values a little bit, it will help us to write in next step. So 0 0 cancels, okay, 78 by 2 is 39, 52 by 2 is 26, okay, 13 3 13s are 39, 13 2s are 26, okay. So 3n equals to 2n plus 2, right. So take this on this side, so 3n minus 2n equals to 2, or n equals to 2. So this will happen for second bright fringe for both of the rights, right. So second bright fringe is the answer, second bright band is the answer. If they have asked you for dark band, then instead of having n lambda you have to use n plus half lambda on left hand side and n plus half plus 1 in our right hand side, okay. So that is the basic difference. So try that and tell me if you find anything different in that case as well. Now we are talking about diffraction. Diffraction is very interesting topic, and it is very interesting because we so far, like we have said that light always travel in a straight line, right. So suppose I have a sharp knife edge, okay, sharp knife edge, and I have a screen here, okay. So a ray of light is coming along this, okay. Now what we are supposed to observe on this screen? So we have two perspectives. First of all, what is our ray optics tells you? Ray optics tells that the ray of light will continue to travel along the edge, and any light which is coming along this obviously gets absorbed, nothing is coming, right. And this ray will travel here, and we should obtain a shadow here, right. We should obtain a shadow here. And what is our Huygens principle is saying? Huygens principle says that every point on the secondary wave front is a source of every point on the primary wave front is a source of secondary wavelets. So if you consider this point as the source of secondary wavelets, that is, this is the primary wave front and this is the source of secondary wavelets, then from there light should travel in all possible direction, and you should obtain a bright band in the darkness of the shadow itself, right. So this is called diffraction, and actually we observe it. If you can place two blades, razor blades, close to each other, and if you light it up with a laser light, you can observe diffraction in your home as well, right. Now the bending of light around a sharp edge is called diffraction. This is the definition of diffraction, okay. And when we send, suppose we have a single slit. So previously we have two slits, double slit. Now similar way we have created a single slit using either you can place two razor blades to make one slit, or if you cut very sharply across the page and you get a single slit, that is also fine. So what is happening here, when light ray is passing through this slit, okay, according to the conventional ray optics, you should get only a very dark, a very bright band when the slit is there, okay, and everything else should dark, right? Everything else should have been dark according to the ray optics. Now when you observe carefully, what you will see, you will observe that instead of getting fully dark, after this central maximum zone, you get a small region of another maximum, okay, then another maximum, okay. This is primary and central maxima, this is secondary maximas, okay, these are secondary maximas, okay. There is a lot of complex theory in the diffraction which is not part of a syllabus, and there were some maximum condition for maximum and minimum in detail was there, but that is also deleted from there, okay. Also in Young's double slit, fringe width is deleted. Fringe width concept is no longer part of the Young's double slit. The derivation for Young's double slit is not there for PU board as well. So if you are thinking whether I have to study fringe width expression, I have to study the how can I find the condition for maxima and minima, that is no longer part of the syllabus. They are all deleted. Only the expression for maximum is there in your syllabus, okay. Nothing else is there, no fringe width, no concept of fringe width is there, okay. Now if you observe that during a diffraction, what we observe, a very central white band, right, and then diminishing secondary bright bands, okay. This is the secondary bright bands, but the intensity is decreasing rapidly. So this will have the maximum intensity, and the intensity of the secondary bands are decreasing rapidly. In case of interference, all the bands, all the bright bands are equally bright. That is the basic difference between interference and diffraction. In interference, all the bright bands are equally bright, okay, all the dark bands are equally dark. In this case, dark bands are okay, dark bands are all equally dark, but bright bands vary intensity as you are moving away from the slit. In fact, for a very sharp slit, you don't get too many bands. After some time all the bands disappear, okay. So that is one of the very interesting thing, interesting concept, but you still get these bands which are actually very interesting, and that proves the wave theory of light. If we are not getting these bands, and then we could have ignored that and we would have said the geometric optics or straight line optics is still correct, but it is not, because diffraction proves it is not correct, right. The interference and diffraction, light energy is redistributed. Now you might ask from where these lights are coming. Also in case of, I said in case of interference that we are getting bright bands, but there was only two sources, right. How you are getting so many bright bands, how you are getting so many dark bands. So what is happening here is that light energy redistribute itself, which is very, very important, okay. If it is reduces in one region, that is dark band, producing a dark fringe, it increases in another region producing a bright fringe. Very interesting concepts, okay. So because it is producing dark fringes here, that means that if there is no obstacle, then the light would have fallen equally on all the points. So what is happening now is light is redistributing itself. Some places they are increasing, producing bright fringes, some cases they are decreasing, producing dark fringes, okay. There is no gain or loss of energy here. In case of interference or diffraction, you are not creating energy, neither destroying energy. It is only a redistribution of energy, which is consistent with the principle of conservation of energy. So it may, some people might ask you, or they might try to confuse you that in bright fringes energy is destroyed, and in bright fringes energy is created, in dark fringes energy is destroyed. Is it correct or not? It is not correct. Conservation of energy is always valid. Okay, now let's look into one problem. In case of Fraunhofer diffraction, now you might not be familiar with the term Fraunhofer, but Fraunhofer diffraction means normal diffraction. Okay, there is one more classification of diffraction that is not part of the syllabus, so we will only discuss normal diffraction, which is Fraunhofer diffraction. It is from 2024 question, and it is not out of the syllabus question, it is part of the syllabus. Okay, in case of Fraunhofer diffraction at a single slit diffraction, not 2024, it is 2023 question. Okay, in case of Fraunhofer diffraction at a single slit, the diffraction pattern on the screen is correct for which of the following statement? Okay, central dark band having uniform brightness on either side. Okay, central dark band having alternate dark and bright bands decreasing intensity on either side, central bright band having dark bands on either side, central bright band having alternate dark and bright bands of decreasing intensity on either side. Okay, so option B and option C are same. I think one of them will be increasing, another will be decreasing. So we know that that as we have seen that when we are observing fringes, okay, the central fringe is bright and there is a dark band as well as bright band alternatively, but the intensity of the bright bands decreasing as you are moving away from the central fringe. So you can answer this. Actually B and C from this given question, B and D both are correct option, but since they are all same, I think there is a mistake by me while typing the question. So it will be increasing in one option, decreasing in another option. So the intensity is decreasing as you are moving from the central fringe. Okay, now let's move on. The last concept of this chapter, very important concept, polarization. Polarization, if you remember, we have talked about when the electron is accelerating. Okay, electron is accelerating, it is producing an electromagnetic wave, right? So it is producing variable electric field as well as variable magnetic field, which gives rise to the production of electromagnetic wave. Now when we are considering electromagnetic wave, we generally say light is traveling in some direction, right? Now also in electromagnetic wave chapter we have learned that suppose light is traveling in this direction, so electric field will be vibrating perpendicular this, and there will be a magnetic field which is perpendicular to the electric field as well as the direction. So both of them, all three of them are perpendicular to each other, so they are like this situation. Okay, so this is the propagation of light, this is magnetic field, this is electric field, like this. Okay, they are all of three of them are mutually perpendicular. Now what will happen, instead of we from now on we will not show the magnetic field, we will only show electric field. For this part only, for polarization only, we will only show electric field, and also not like this, we will show electric field using only arrow. Okay, so if the light is propagating in this direction, then electric field is in this direction, right, perpendicular to the direction of light. Now we say light is traveling in this direction. Now how many possible perpendicular direction is there to this line? There is a perpendicular direction possible in this line, there is a perpendicular in this line, in this line, in this line. So if you consider a line, in this line there are multiple possible perpendiculars, right? All lines that if you consider this, all points, infinite number of perpendicular is possible for a single light. In fact, for a single light there are numerous electric field is working to produce one ray of light. Okay, so for one ray of light propagating in a particular direction, there are hundreds of electric fields propagating vibrating in the perpendicular direction of the light propagation, right? So what is this? This is, light waves are transverse in nature, right? So the electric field associated with the propagating light wave is always at right angles to the direction of propagation of the wave. Light waves having electric field in all possible direction is called unpolarized light. So this light where electric field can vibrate in all possible direction, okay, it can vibrate along this direction, it can vibrate along to and fro from this direction, up and down, or any other angular direction, but the angle between these two are always 90 degree, then that light is called unpolarized light. So unpolarized light can have all possible electric field for a particular direction of light, right? Now if an unpolarized light wave is incident on a special crystal, okay, remember that special crystal called Polaroid, okay, then the light wave will get linearly polarized with the electric vector oscillating along the path axis of the Polaroid. It is called polarization. Now let us understand this in a detail. So what is the meaning of that? So light has had all the possible electric field vibrating in all possible direction. Now you placed a crystal, okay, there are few different crystal. One of them is quartz, you might have heard it. Quartz is basically a crystal which is there in our old generation watches, okay, and if you are a Jedi fan, you know that the lightsaber is built on quartz, right? So quartz is basically a crystal, okay, and when it cut in a particular way, okay, they can have a particular way to emit light. So if this is a crystal, then light rays which are actually having electric field only vibrating in this direction, they are allowed to pass, okay, they are allowed to pass. Any other rays, any other light rays vibrating in any other direction, they will be absorbed by this crystal. The crystal will absorb anything which are not vibrating in this direction, everything else will be absorbed, and only light ray which is vibrating along this path, this is called path axis, the light ray will pass, only the electric field which is vibrating along this direction, they will pass, every other light electric field will be absorbed, okay. Now this is called polarized light. This light is now only having only one direction of electric field associated with it. So this is called polarized light, this is called unpolarized light. Now as you know that for each vibration of electric field, any vibration of electric field, there will be a light, but they are perpendicular. It is a three-dimensional thing, obviously. So if there is a propagation of light and this light is allowed, this light is not allowed, so what will happen? The intensity of the light will be reduced, right? So after polarization, the intensity of the light will be reduced. So what will happen to the intensity? The intensity of the polarized light is half of the unpolarized light. Very important concept. So this light, if the intensity of this light is say I or I naught, generally we denote it by I naught, then the intensity of the polarized light will be I naught by 2. Okay, and this has a lot of important applications, the polarization of light. First of all, if you are wearing a sunglass, costly sunglass, they have a coating on top of your eye. That coating is actually a polarizer which allows light to pass only for certain angle. So that's why you feel soothing, your eyes are soothed, and the intensity of the light is also reduced, so you can see it clearly and your eyes don't feel stressed, right? This is one. Secondly, if you ever watched a 3D movie, okay, if you ever watched a 3D movie, there are basically consisting of two different polarizer. Each of your eyes having different polarizer. One is along like this, another along like this. Okay, so one is allowing light to pass through in this direction, another one is allowing light to pass in this direction, and that is creating a 3D effect. So 3D glasses, next time if you watch a 3D movie, you can collect the glass if it is a paper based one, and they are allowed, if they allow you to carry it back, you can carry it back and you can do some testing along with this. Okay, so 3D movies are basically a kind of polarized glasses. Very important law is Malus law. Okay, So Malus law is I equals to I naught cos square theta. So suppose you are light is already polarized. You have a polarized light. You have a polarized light. It is not unpolarized light. Remember that here I naught is the intensity of the polarized light, and you have a polarized light which is suppose vibrating along this direction. Now you have another polarizer which does not have light axis exactly parallel to this. Then what will happen? If they are not exactly parallel to it, there will be an angle theta between the pass axis of the second crystal and the angle of the original wave, right? So in this case, will it absorb everything? Will it absorb all the light? No. If the angle is not exactly 90 degrees, so the light will not be absorbed. If the angle is exactly 90 degrees, that is this axis has exactly 90 degrees. This is the electric field vector, this is the pass axis, then intensity will be 0. Okay, if the angle is 90 degrees, then the intensity will be 0. But if the angle is not 90 degree, the intensity will not be 0. The output intensity, suppose the input intensity is I naught, output intensity is I, then the output intensity is given by I equals to I naught cos square theta. Very important formula, and based on this formula there are a lot of questions comes from this formula. So let's look into one such problem. This is from 2024 question paper. Okay, 3 polarized sheets are coaxially placed as indicated in the diagram. Okay, pass axis of the Polaroids 2 and 3 make 30 degree and 90 degree with pass axis of Polaroid sheet 1. Okay, I naught is the intensity of the incident unpolarized light entering the sheet 1, the intensity of the emergent light through the sheet 3. So first light is entering through this with the intensity I1. Okay, so what will be the intensity of the light after it passes through the first Polaroid? After it passes through the first Polaroid, the intensity will be I naught by 2. Someone has already written the answer. So I naught by 2 is the intensity of the emerging light from the first Polaroid, right? Now here the angle between the this light and the second Polaroid is 30 degrees, right? So what is the intensity of the light after it passes through the second Polaroid? So let's say I2 is equal to I naught by 2 cos square 30, right? Cos square 30. So what is the value of cos 30? Cos 30 is root 3 by 2. Root 3 by 2 is square. That means 3 by 4. This is I2. And what will be I3? Now what is the angle? This angle is 90 degree. So this is very interesting. Okay, if you say okay, the angle is 90 degrees, so now it will be 0 degree, right? Cos 90 is 0. So this angle is 30. This angle is 90. So what is the angle? This angle is important. What is the angle between two consecutive Polaroids? The angle between two consecutive Polaroid is 90 minus 30. That is 60. Okay, so this is important. So if you see, okay, this is 30 degrees, so cos square 30, okay, 3 by 4. Now this is 90 degree, cos square 90. Oh, 90 is 0. No. Here you have to find the angle between two consecutive Polaroids. That is, if this angle is 30, this angle is 90. So they have given the angle based on the same axis, right? So you have to find the angle between two corresponding axes. So I3 will be I3 will be so if you write it like that, 3I naught by 8 times cos square 60 degrees now. So what is cos square 60 degree? Cos 60 is half. So cos 60 is half and half square is 1 by 4. So it will be 3I naught by 32. This is the intensity of the emerging light. Okay, 3I naught by 32 is the answer. So if you by mistake if you mark 0, you will get 0 marks, right? Now time for today's homework. You can read the question. I am reading the question for you once. An unpolarized light of intensity I is passed through two Polaroids kept one after another with their planes parallel to each other. The intensity of the light emerging from the second Polaroid is 1/4. The angle between the pass axis of the Polaroid is. So here they have given the intensity, okay, not 1/4, it will be I/4. It will be I/4. Thank God I have seen the question. Okay. So what will be the angle between the pass axis of the two Polaroids? Very interesting question. Try to solve it. Mention that what you find. Next question. In Young's double slit experiment, slits are separated by 2 mm and the screen is placed at a distance of 1.2 meter from the slits. The light consisting of two wavelengths 6500 angstrom and 5200 angstrom are used to obtain interference fringes. Then the separation between the fourth bright fringe of two different patterns produced by the wavelengths is. This is also very interesting question. So you have to solve these two questions and mention the answer in the comment below. I am not getting any answers for last few videos, so don't forget to mention the answers for these two homework questions. I will be back with the answer of these two questions along with the few more questions tomorrow with PYQs. In the PYQ of this chapter, these two questions are given in the PYQs, so I will be not solving these two questions in upcoming video. I will be solving along with PYQ tomorrow. Tomorrow I will be bringing PYQ for wave optics chapter. So don't go anywhere. And if you are thinking that how you can get all the videos available at one place, yes, we have this playlist. You can visit our channel, then you can bookmark this playlist, KCET 2025 physics series, where we are completing all the chapters within 100 days. So by December 1st week we will be completing all the chapters, and then from there onwards we will be only doing revision. Okay, by 100 days, that is first week of December, we will complete all course will be completed by December. There we will be completing all the chapters. From there on we will be only doing revision and more tests. Okay, so you can see all the videos, that all the course that we are currently doing is available in this bookmark, available in our channel. So you can go there and watch them at your own time. Also you have to join our WhatsApp group if you want to participate in KPL every Sunday. And if you think that this is helpful, share it with your friends and subscribe to our channel. I will be back with PYQ of wave optics tomorrow. Till then, tata, bye bye.